Hi, in the first mini lecture concerning decoders, I introduced the most common one, which is called simply decoder. So without any additional information. So if you see this name, that means that it is a binary to one of n in general. N must be stated. N is 2 in our case. That works. For the other decoders, and including the opposite decoder I will introduce in a moment, you must deliver additional information concerning the input code and the output code and the rule how to cast one to another. Okay, so the first topic of this mini lecture is the opposite decoder. So you must name it one of n two binary decoder. And you must give n. N equals 4 in this case, which means 4 input decoder having 2 outputs. And the rule is the opposite. As you remember, the number of inputs of the common decoder was n, and m was equal to the power of n. In this situation, we define the number of inputs being n, and the log of this is the number of outputs. M is equal. Okay, so this was introduction only. So let's construct the truth table for this device. So you've got 4 inputs, x3, x2, x1, x0, and 2 outputs, one y1, one y0. And because it is a 1 of 4 code, and here is binary code, and the rule is exactly the same, similar as in the case of common decoder. So you've got all the valid sequences on the input sequences, and here you will have other cases. And the interpretation is the following. You've got 1 on input x3, that y3 in binary is present on the output. It is simply 3. x3 is equal to 1. In the second row, 1 is present on x2, that's why 2 in binary is generated on the output, and 1 and 0. In the other cases, we assume that they never occur. We assign don't care symbols. Okay, in the real device, there aren't. Yes, they don't occur. But in the case of constructing, when you construct the truth table, you must put don't cares in these rows, in these places where you can do it. Okay, so it is very important for minimization. And then it is a function of 4 variables. You can minimize it, use it y1 and y0 using the Carnot map. And let's do it for y1. Y0, I propose that you will do the second minimization process. I will show you only the first one for y1. So you must use gray code in columns and rows. Don't forget it. Yes, please remember. Yes, gray code. And the fastest way of filling in this K-map is to find these 4 cases. Okay, and the remaining will be filled with don't cares. Okay, so y1000 is the first one. 1000, it's this cell. It is 1. The second is 0100. 0100 is here. The third is 0, 0, 1, 0, and it is the value of 0, 0, 0, 0, 1, 0, sorry, it is 0, and the last one, 0, 0, 0, 1, and 0 as well. The remaining cells in the K-map are labeled with don't care states, and you in the phase of minimization, you simply combine as many don't cares to the given one or given 0, depending on what you are interested in. I mean the form, sum of products. Let's assume we will be minimizing for 1. So you expand, yes, you can expand to find a group which the largest number of elements by combining don't cares with ones, where it is where it gives you the more compact version of the resulting function. So you are looking for the bigger group. So by doing this, you assume that these don't cares will be implemented in a real device as ones, these ones, and these outside the groups will be implemented as zeros. In a real device there aren't don't cares. Okay, so from the first, I mean this one, you get what is static x2. From the second group of 8 elements, you get the static value x3. That's all. Very short, compact, very cheap solution, and a single gate is needed to generate y1. Do the same for y0 and find it. And they too don't depend on x0. And this is the conclusion. And so this signal doesn't need to be connected even, okay, the x0. So, but verify it at home. Now I'd like to switch to a bigger one, and show you another approach, the other approach without minimizing using K-map, because the number of inputs is too high to do it. Let's suppose you've got 8 input decoder. It is a 1 of 8 code. So you've got a 7, 0, x7, x6, etc., x0. So how many outputs are there? 3 outputs, denoted by y2, y1, y0. And the truth table is quite big, containing here 8 inputs, and you cannot minimize it using K-map. Okay, K-map up to 4, 5 maximum variables. And how to face this problem, how to solve it, how to find the minimized solutions for y2, y1, y0. Let's first fill in this. It is a little bit time-consuming process. 1, 0, 0, 0, 0, 0, 0, and must be patient, waiting for my drawings. Okay, then 8 rows, because you've got 8 variables on the inputs, 8 inputs simply. The number of valid sequences of the code is 8. And now the rule is the same as before. The number of the input on which there is 1 is presented here in binary. This is index 7, so 7 is here. It is 6, sorry. It is 6, 1, 1, 0. it is 5, 1, 0, 1, it is 4, 1, 0, 0, and so on. 3, 2, 1, and 0. That's it. So the problem is how to find y2 without performing minimization. Okay. Look at the columns. What is it? Okay. I've forgotten about the other cases. Other cases. How many other cases? Don't curse as before. How many other cases? We've got 8 out of. You've got 8 out of 256 minus 8 gives you 248 other cases. A lot of them. A lot of them. So, and looking at these, yes, you can see, you can notice that there is a single one in each row. In this part of this table, not this. We are not interested in this part, so this is not important. Not important. We are only scanning these lines, okay? And we'd like to get these 4 ones and zeros here, okay? How do we do it? Look at this. It is very important that this column. Each of these input columns, the input variables, has a single one in different positions. So in order to get 1, 1, 1, 1 in the first 4 rows, you simply combine, you simply add these values, these variables. If you add these 4 columns, you get 1, 1, 1, 1, because there are ones here, and zeros in the remaining positions. Okay, 1, 1, 1. That's exactly y2. So you're simply guessing or scanning or deriving this heuristically, looking at and knowing that you add two bits, 1 is 1 and 0, you get 1. Okay, so in this situation you've got an x7 for y2 plus x6 plus x5 plus x4 and nothing more. Okay. Here we don't know exactly what we get, but for these positions that are valid for valid sequences, you get this pattern 1, 1, 1, 1 and then 4 zeros. What about y1? We do exactly the same. So looking at this, the first one in these 2 rows comes from the first 2 variables, x inputs. x7 plus x3 gives you 1, 1 and zeros here. But you need also 2 ones here, so you must find that this is at x3 1 and x2 1. So x3 and plus x2. What about y0? y0 is 1, 0, 1, 0, 1, 0. So the odd indexes are needed. So x7 plus x5 plus x3 plus x1. In each column, for each variable, you've got 4 ones, but in different positions in general. So these are for sure minimized version. Minimized equations. Okay, so it is the first example of a heuristic approach. Yes, not having an algorithm, a general algorithm. A general was minimized using K-map. You couldn't do it. So you follow another rule because of the simplicity of the shape of the pattern of this truth table. Okay, thank you.